Physics Notes, Unit 4.4, basically examples of Newton's three laws of motion. So applying Newton's three laws. First law is an object at rest stays at rest, an object in motion stays in motion at constant velocity unless acted on by a net force. The second law, summarized, is F net equals ma. Or a lot of times they start off as saying A equals F net over m. Same law, just reformatted. And then the third law, for every action, there is an equal and opposite reaction. And these three laws will come into play here in these examples, most specifically the second law and the third law, but they all apply always. So let's practice. All right, so we have this example. And, okay. It's two boxes sitting on a floor. Box A has a mass of 3 kilograms and box B has a mass of 5 kilograms. So I'm going to draw this situation. So here's the diagram. It's not a free body force diagram yet. We will need to do that. But box A is a smaller mass. It doesn't necessarily mean it's smaller in size, but I'll just draw a smaller mass, smaller in size, even though it could be bigger. Depends on the density of the object. Because the mass does not necessarily correlate to the volume of something. A pillow would have a large volume, small mass. A bowling ball might be a little bit smaller than a pillow, but with more mass. Anyway, we're pushing on box A. These boxes will slide to the right. Right now there's no friction. We'll talk about that in the next unit. And these are going to accelerate to the right. And it asks you to draw a free body force diagram for each box. All right, so let's do that. That's part A. And once again, you may want to pause your video to draw all this. But let me talk about some of the subtleties here. Let's look at box A. Box A, and like we've done before, there'll be a force of gravity straight down. We could actually calculate that. You could actually almost, well, you could do a rough approximation in your head because it's 3 kilograms. The weight will be 3 kilograms. The mass times 9.8. But if you take 9.8 and round it off to 10, basically the force of gravity straight down on box A is roughly 30 newtons. You could put that right on there, 30 newtons. And therefore the support from the table, which is called the normal force, would also be 30 newtons. So this force up here would be 30 newtons. I would just put that on there normally, but I just want to illustrate a few things with these symbolisms. When I label a diagram, in the generic sense, if I don't put the numbers on there, or you could put the numbers on there as a shortcut, 30 newtons here for both those forces, I use the letter F for all my forces. In the book, just so you know, like this force right here, the one that's pointing up, they will label that as capital N for normal force. I don't necessarily like that because it looks like it might stand for newtons. I label everything, all of these forces are forces, so I call them force. And I use subscripts to tell you what force it is. And, well, here, this is the 19 Newton force. And it's, you know, you could put it anywhere, but I like to put the tail on the center of mass here. That's the same Newton, the same force that's pushing on box A. It's literally somebody's hand or whatever touching box A, pushing box A. That force is not being applied to box B. It's being applied to box A only. We'll come back to that on box B. But here's kind of the tricky one. This blue, I have labeled blue here. It's the force of box B pushing back on box A. Because if you go to box B now, once again, there'd be the force of gravity, which would be 50 newtons. The normal force, 50 newtons. Once again, in the book, it'll say N equals 50 newtons. And I use the subscript here. It's the normal force on box B. The shortcut would be just to label that 50 newtons. Close enough. Okay. But literally, box A is touching box B. Anything that's touching you is exerting a force on you. And it's pushing box B. So that's what's pushing box B, box A, not the 19 newtons. So one way to describe that in symbols is the force A on B. the force that box A applies on box B. Some books will just say FAB as subscripts. They will get rid of the word on there. In fact, any force, kind of like when we first talked about Newton's third law, you can talk about the two nouns, the two objects involved, and then the one preposition between them. For example, this force of gravity, that's the force of the earth on the box. Force of earth on box, pulling the box down. This would be, this up here, this F normal, you could also label as force of floor on box. You can change all these naming systems, these symbols, to a three-word prepositional phrase, basically, or the word on is the preposition you always use between the two nouns. Go back over to here. Like this 19 Newton force. You could say that that is the force hand on box, if there's somebody's hand pushing the box. Hand on box. Hand pushing box, if you want to get rid of the preposition, but it's three-word phrase. Hand on box. In fact, all these forces are here. That's the definition of a free body force diagram. You're only drawing the forces that are on the box. Not that the box is exerting on other things, because the box is also pushing down on the earth. I don't care about that. Although over here I did care about this force, but because of box B, it's the force of A on box B. So this blue force here and the blue force over there is an illustration of Newton's third law. If box A pushes on box B, that's this over here, then box B pushes back on box A. Those two forces are the same size. So you could just say, well, whatever they are, 30 newtons, 30 newtons, 20 newtons, 20 newtons, they're both the same force. You could get away with here just calling them F. And I'm kind of going to do that as I go forward here to simplify the problem. But right now I'm giving you the more detailed explanation. So these are indeed the free body force diagrams for these two boxes. And when we have friction, we have to then add that in. That'll, like I say, be a later unit. So the way you approach these Newton's three laws problems is you really kind of focus on the middle one. You apply F net equals ma. Let me do that. Okay, so what I have done here is I'm applying Newton's second law to each box individually. There is a shortcut I'll show you about in a few minutes here. But for box A, F net, box A, equals mass of box A times the acceleration. And I could have said acceleration of box A, but I'm just going to use the letter A for acceleration in general here because both boxes have the same acceleration, so I don't need to differentiate acceleration of box A as a subscript. Although the masses are different, that's why I have mass of A and mass of B over here, because they have different masses. And they have different net forces, but they both have the same acceleration. That's why I'm just using the letter A without subscripts in these two equations, and that's basically what will connect these two equations and help us solve this system algebraically. So here are some tricky parts now. The net force on box A, I know the whole system is going to accelerate to the right. So my rule is this, to be consistent all the way through when we apply Newton's second law, especially when you have two forces, you take the big force minus the small force in the direction that it's accelerating. I know it's accelerating to the right, so I know 19 is bigger than this blue force here, and I'm then now summarizing that, writing it more concisely as FBA. That means the force of B on A. That's the same force there, that blue force. And once again, I could have just called that F here because it's the same F in both equations, even though here I have F box B on A, this is A on B, they're the same force. So I could really drop the subscript there as well and just call that F. That's what I'm really kind of looking for in this problem, and one of the main things I'm looking for. But it's big force minus the small force. Net force is going to be like 10, 11, 12, 13 newtons, somewhere in there. All right? But here I have an equation with two unknowns, so I can't solve that yet. Over here for box B, I have two unknowns as well, but there's only one force. That one force is the net force, so I don't need to do any subtraction. There's only one force causing box B to accelerate. That's the force of A pushing on it. So once again, because of Newton's third law, FAB and F sub BA are the same force. So I can substitute one for the other. That's what I'm going to do here. So yes, what I've done is I've taken this F sub AB, which is 5.0a, and substitute it in over here because it's the same force. According to Newton's third law, FBA and FAB are the same numerical value. So this is minus the 5.0a that I just plugged in. Add the 5.0a to both sides, you get 8.0a, divide by 8.0, and you get the acceleration of the system. It's each box. That is the answer to part B. Both boxes have that acceleration. Now, there is a shortcut you could have taken. Some of you maybe have done problems like this before. Just so you know, you can't always take this shortcut. But one shortcut would be to treat it as one big 8 kilogram mass. Let me outline that. So here I've drawn this as one big box, 8 kilograms. And the book also gives some more examples about defining your systems, but when they're doing that, what I'm kind of focusing on are my free body diagrams, which are my system. And I'm trying to keep it simple. Here's a simple way to do your system. Make this all one 8 kilogram box. Well, the 19 newtons then is applied to that system. It's hitting box A, but now box A and box B are combined together, and that force is applied to that big box. And then I did the computation. This is roughly 80 newtons of force of gravity down, 80 newtons up. Those don't matter. That would be an F net of 0. So the only F net is this horizontal force. And these are not proportional right now. Sorry about that, because the 80s should be really, really big, and I can't draw them that big. They're, 4 times bigger than the 19 newtons. Or I could have drawn the 19 newtons and much shorter. I'm not going to get that picky, but I could have drawn that shorter. I wanted to draw it big enough so you could see it right there, but I could have drawn it as a very short vector there. Probably should have. But anyways, F net equals ma. Well, the net force here is 19 newtons, and the mass is 8. So there you go. That's your shortcut. So once you get used to these, there are some shortcuts. You can't always take the shortcut, but that is a shortcut. All right, now this problem also has more parts. We have to figure out actually the force between these two boxes. I think that's part C. The action-reaction force. That's that blue force, F sub BA, F sub AB. Well, once we have the acceleration calculated, we can get that force by either using really this equation right here or this equation over here. Either equation should give us the same answer. For example, I'm just going to plug into this equation. I know A now is 2.4. So if I take 2.4 times 5.0, that gives me that force, that surface between the two boxes, the interaction force, the Newton's third law force. So let's do that. So what I've done over here on the left, part C, I've taken this equation from way over here. This was the F net for box B. The force AB is the net force, equals the mass times the acceleration, which we just computed as 2.4. So I just plug that in. And 2.4 times 5.0 to 2 sig figs is 12 newtons. If you want to give a 3 sig fig answer, that's fine. It's really not proper, but 2 sig fig answer, 12 newtons rounded off. Then I took this equation right here, okay, and brought it over here and just plugged in the 2.4 for A. And I get the same answer. In other words, the 19 newtons here minus FBA, which I'm looking for, equals 3 times the 2.4. I'm assuming I don't know what this is yet. But if I do the math here, and once again, I'm rounding off the 2 sig figs here eventually, it's going to be 19 take away 7 is 12 newtons. It comes out to be 12 newtons. It has to be consistent, otherwise something's wrong, because these are the same force. Whether I label them F sub AB or F sub BA, they're the forces that each box exerts on the other box. I could just call it F if I want to. That's the interaction force. That's the Newton's third law pair of forces for every action equal and opposite reaction. Part D now, I need to find the net force on box A. Let's do that. Okay, so, and there's 2 ways to get the net force on box A. You could just do Newton's second law. F net equals ma. The mass of box A, it's a 3.0 there, times the acceleration 2.4 is 7.2. Or you can simply just look at the diagram, back at the diagram. There's a 19 Newton force pushing, and then we figured out that this was 12 to 2 sig figs. So you could just say 19 minus 12, that's also 7 to 2 sig figs. 7, but 7.2 if you go to 2 sig figs. And the net force on box B, there's only one force causing it to accelerate. That's the 12 newtons. So don't need to subtract it all. The other 2 forces, the 80 and the, well, not the 80, the 50 and the 50 would have canceled out, up and down. So there's only one force acting to cause the acceleration, that is the net force. It's kind of nice when there's only one force that causes the acceleration. That is the net force. Okay, example number 2, an elevator. So now we're talking about the elevator, not a person in the elevator. So we want to focus on, well, I'm going to draw it as a box. Let me draw this. So I've pretty much done part A here. Here's the diagram. The red box, you don't even need to draw. That's the elevator. There's a cable. So here's the center of gravity. And I did a preliminary calculation, but on further problems, you can just do these in your head, basically. The weight is the mass times the acceleration due to gravity, which is 9.8. You can always round that off to 10. Just do that computation in your head. 10 times 1,800 is 18,000 newtons. So the down vector, the weight of this elevator, is 18,000 newtons. If you want to still label that as F sub gravity, that's what it is. It's computed. So I just put the number on there. It's a little faster, and it's an important number. The cable is holding the elevator up. It's keeping it from, freely falling and crashing and destroying itself or hurting anybody inside the elevator. So force of tension, a lot of books will just put capital T for that. I end up usually just putting F sub T. Like I said before, I always like to label all forces in a diagram with an F for force. They're all forces. Be careful here. This is just a note to myself and to you that the acceleration, it's accelerating down at 0.82 meters per second squared. That's not a force vector, so don't put it on the diagram directly. It's just a guide to help me with applying Newton's second law. Over here, F net equals ma. So I will now plug in there. My rule, once again, is you look at your diagram, and it's kind of nice when there's only two forces. It's even nicer when there's only one, because then that is the net force. But with two forces that are opposed in direction, you look for the bigger one. And I know this one's the bigger one because that's the direction of the acceleration. So that's the bigger force. So I take 18,000 minus the smaller force to get the net force. So that expresses the net force. Big force minus small force equals the mass times the acceleration. So I don't put any negatives in the diagram or in the calculation per se. The negatives are taken care of with just taking big force minus small force. Like we did, I think, with a ball problem earlier. If the two forces are in the same direction, you just add them. But when they're in opposite directions, you subtract. So that takes care of any negatives that might crop up in the actual problem. Now it's just doing the algebra. The sig figs come out kind of funky here. 1,800 times 0.82 is rounded off. It's 1,500. And then I have to round that off to 2,000 to combine it with the 18,000. If you want to go to 3 sig figs here, you can. You would have gotten like what 16,500 newtons. I would take that. I wouldn't take any points off for sig figs there. But technically speaking, round this off to 2 sig figs, or one sig fig to add it or subtract it from the 18,000 to get 16,000. That's the tension in this cord when it's accelerating downward at 0.82 meters per second. Now let me set up part B here. All right, so I've drawn all this out. So here we have, it's the same looking diagram, except for now the tension force is bigger than 18,000 newtons because it's accelerating up. So I know the bigger force is this one. I'm not going to get real picky about how long you draw those arrows, but technically this arrow should be, this force vector arrow should be a little bit bigger than that one. The main thing is which way they point. So we apply Newton's second law, F net equals ma. Once again, to be consistent, take the big force minus the small force. I know it's accelerating up, so F tension B, and you could even leave off the subscript B here, and you'll be fine. But we are on part B. But big force minus the down force, up force minus the down force, equals the mass, 1,800 times our known acceleration of 1.2. So 1.2 times 1,800 is 2,200. And once again, if you want to do 3 sig figs, you get 20,200 newtons. I just did 2 sig figs, and the way I show that, some books do this, not many anymore. That's not really a mistake there. That little symbol just above that 0 just means that's a sig fig there. You don't need to do that either. Don't need to know that. But if you put 20,200 newtons, fine. Don't go to 3 or 4. Don't go to 4 or 5 sig figs though. But technically it's 2 sig figs, 20,000 newtons to accelerate up at 1.2 meters per second squared. And finally, part C, what if it's moving with constant velocity, which is what the elevators do most of the time. They only accelerate at the very beginning or end of the motion. Well, what has to be true is, if it's constant velocity, this problem is almost so easy it's hard. There is no net force. In other words, all the forces have to balance. It's the same diagram. Well, then the force of tension has to be equal to 18,000 newtons. It has to equal the weight. Now, let's think about this a little bit. If like in part B, if the elevator got up to its speed, whatever speed it needs to get up to, because there was this big force, and then through the mechanics of the motors or whatever, now what it does is it changes the tension in the rope from 20,000 to 18,000, and what's going to happen is the elevator will maintain its speed. Once it's already up to speed, it will maintain its speed because the F net is 0, but it will be the constant velocity, like in Newton's first law. If it's up to a certain velocity, if there's no net force, no unbalanced force, it will maintain that velocity, whatever it was, 5, 10 meters per second, whatever elevators max out at. Same thing would have been true in part A. It would have sped up a little bit, and then the motors would change the tension back to 18,000, so it has a constant velocity for most of the way down. So if the elevator is at rest, like at the bottom, if the force of tension is only 18,000 newtons, well, it won't get going. There's no net force. So you have to have a big force to get it going, but once you get it going, then the force matches the weight to keep it moving at the constant velocity. All right, number 3, which will then require some review of uniform acceleration as well. Let me draw this diagram. Here's the free body force diagram. And I did the computations in my head, as you, I hope, now can do. If the mass is 2,100 kilograms, the weight is 2,100 times 10 is 21,000 newtons. So I just put that right on the diagram. Or you could say force of gravity. It really won't be that important, this problem, because you won't be using it. We're looking at the left and right motion, not the up and down motion. And then the road supports it with 21,000 newtons, roughly 5,250 newtons of force at each tire. Once again, not important. But if the car is moving to the right, once again, that's a velocity vector. Don't put it on the actual diagram. We want forces only on the diagram. But if I'm moving to the right, when you hit the brake pedals, it has to apply a force to the left to slow you down and stop you. So you could call this force of brakes, or you can just call it F in this problem if you want, or force of stop. It's a force that stops the car, acting through the brakes and the tires and so forth. Doesn't really matter all the particulars. There is a force, a net force that stops the car. And we're ignoring air resistance here. In general, you do that unless it tells you otherwise. So there is only one force, that is the net force. But if you write down the F net equals ma in this problem, what you'll see is all you know is the mass. You don't know F net, which is the force of brakes, and you don't know the acceleration. You know the velocity. So don't plug the velocity in for the acceleration. That is not the acceleration. So in this equation right now, I have 2 unknowns, and that's the only equation I really have so far with Newton's second law. So I can't really do much with that until I go back and review my uniform acceleration. I'm going to come over here and look at these equations and write down what I know. In other words, I know that V sub 0 is 25 meters per second. This car is going to come to a stop, so its V final is 0 meters per second. And the time is going to be 4.5 seconds. So if I look at those equations, those are all given. All these things over here were given in the problem. So I know I have to bring the car to a stop. I think the third equation will allow me to calculate the acceleration. So this is a review of uniform acceleration. The third equation being V sub f equals V initial plus AT. V sub f is 0. V initial is 25 plus A times 4.5. This is really the definition of acceleration, the definition of average acceleration. That's where that equation comes from. But just plug it in and you get the acceleration, technically a negative number here of negative 0.56 you don't need to put the negative on there, but just be consistent with the math. That's a negative. The negative is only a directional thing. It means to the left. The force will be to the left as well. So when you have linear motion, the negatives are only a directional thing. You can include them. The only time it's really important, like we said with vectors, is when you have the components. Make sure you write those down. But in the diagrams, we take care of all the directional stuff in the diagrams. So now we have the acceleration. We have, going back up to the F net equals ma over here to the right, the F net will be the force of brakes, is what we're looking for, equals the mass of the car, which is 2,100 kilograms. It's 2,100 times the acceleration. If you want to put the negative in that says the force will be negative, you do not need to put a negative in there. I'm not going to do that right now because the direction is on the diagram. It's to the left. The car is moving to the right in my diagram, which was somewhat arbitrary. So the force of the brakes to stop the car, assuming everything is uniform, is 12,000 newtons to 2 sig figs. All right. If you want to say negative 12,000 newtons, I'm not going to dock you for putting a negative on there. It's just they're just looking for the actual magnitude of the force to stop the car. All right. That's an application, a bunch of applications of Newton's third law, and we will practice a little bit more in coming lessons.